Good day, I'm Dr. Wiggins and I hope you are keeping well. This will be the first of two videos on Unit 3.6. Today I will tell you the story about the gradient in 2D. Now, to kickstart, remember how do we calculate directional derivatives of f at the point? If the point is AB and we want to go in the direction of unit vector u, we get a limit. We calculated the limit as h going to naught of fa plus hu1, comma b plus hu2 minus fab over h. Now, as you all know, it's a lengthy calculation to calculate the limit. So the question I want to ask today is there an easier way to find the directional derivative of f at a specific point in the direction of u? And the good news is the answer is yes. And how we do this, we will turn it into a theorem in a moment. But before I tell you what the theorem is, I need a little definition. So let f be a function of two variables with domain D, which is a subset of R2, and it's an open set. Now, if f partial x and f partial y exists at some point AB, which is in the domain D, then we define the following 2D vector, grad f, where the first component is f partial x at the point AB, and the second component is f partial y at the point AB. We call this the gradient of f at the point AB. And now to answer the question, is there an easier way to find the directional derivative? The good news is yes. And the answer is in Theorem 95, and it goes as follows. Let f be a function of two variables with domain D, which is a subset of R2, which is open. Let u be a unit vector. If f is differentiable at AB, then we can use this theorem. And then we know that the directional derivative of f at the point AB in the direction of u exists for any direction u, and we have a neat little formula. The directional derivative of f at the point AB in the direction of u is a dot product. It's a dot product with u with grad f at the point AB. Now, the proof is an exercise, so give it a go if you are interested in how this result came to be. But let's see Theorem 95 in action. So the example I'm taking is example 96. So consider a function of two variables, x squared y minus y cubed plus x. So we want to calculate the directional derivative of f at the specific point 32 in the direction of u, where u is any unit vector, if the derivative exists. All right. So first we're going to establish that all of the directional derivatives exist. After doing this, we are going to find a nice expression for the directional derivative in the direction of u, where u is any unit vector. Now, remember we learned earlier that if a function is differentiable at the point 32, then all the directional derivatives exist. So let's quickly prove that all the directional derivatives exist. So let's start with at the point xy. That exists, and we have an expression for that. So we differentiate each term. The derivative of the first term is 2xy. That the second term is 0, and this one is 1. Likewise, if partial y exists, differentiate the first term with respect to x, we get x squared. If we differentiate the second term with respect to y, we get minus 3y squared. So fx and fy exist on R2, and f partial x, f partial y is continuous on R2. So we have 4 parts here, and this is a reminder that we can then say by theorem 67, it is differentiable at any 2D vector xy. Thus, it is differentiable at the point 3, 2, which is what this question is about. Now, why is this bit of work important? Let's quickly have a relook at Theorem 95. You can only apply Theorem 95 if you know that f is differentiable at the point. So we have done the condition that f is differentiable at the point. So now we can say that all of the directional derivatives exist. And not only do they exist, but we have a neat little formula for it. Alrighty. So now we can continue and we can say that by Theorem 95, the directional derivative u of f exists for any unit vector u. All right. So now we're going to find an expression for this. Alrighty, so first we're going to say, okay, I'm going to need grad f. So remember that grad f, if f is a function of two variables, grad f is a t vector. First component is f partial x at that point and f partial y at that point. So the first component is 2xy plus 1, and the second component is x squared minus 3y squared. And now we're interested in grad f at the point 2. That's going to be 2 times 3 times 2 plus 1 times 3 squared minus 3 times 2 squared. This works out to be 13, and this works out to be minus 3. And now we can say that the directional derivative f at point 3 in the direction u is grad f dotted with the unit vector. See how easy it is now to work out directional derivative. This vector we worked out is 13 minus 3 using the convention that this is a vector. The first component is u1, the second component is u2. And we know how to work out the dot product of two vectors in 2D. 13u1 minus 3u2 in that story. All right, that was pretty easy. All right, I'm not going to do example 97. I'm going to leave it for you to do. As a little hint, remember a unit vector u is unit if and only if the first component squared plus the second component squared is equal to 1. So give it a go. Alrighty. Now, if we know that all the directional derivatives exist, we want to know, is there a bound? I mean, is there a certain direction in which the directional derivative is the most and the directional derivative is the least? And the answer to that question lies in theorem 98. If f is a function of two variables with domain D, which is again an open set, assume that f is differentiable at the point AB, so therefore all the directional derivatives exist, and grad f is non-zero, so these are all the conditions, then we define the following special vector u. U is defined as grad f divided by the norm of grad f, and then what we are saying is the following, that if you look at all of those directional derivatives, and if you go in this direction u, then the directional derivatives will be the most or the maximum. And if you go into the direction of minus u, then the value of the directional derivatives will be the least. And if v is any other direction which is not u or minus u, it is somewhere in between. So not only does this theorem tell you that the directional derivatives are bounded, what is the most and what is the least, and which direction do you get the most and which direction do you get the least, but it also tells you that if you travel in any other direction, the value of the directional derivative will be in between these two values. So in effect, we found the most and the least value that the directional derivative can be. So let's quickly see theorem 98 in action. So here we have a function of two variables, x times sine x minus y. And let's read the question. We want to determine the direction in which f increases the fastest. So this is clearly a directional derivative at the point pi 0, and find the maximum rate of increase of f at the point AB. All right. Now let's first establish again that all the directional derivatives exist. All right. This is important. So f partial x. So here we've got to use the product rule. So it's the derivative of the first term times the second term plus the first term times the derivative of the second term. And now we calculate f of y. So here we don't need product rule. So if you differentiate, derivative of sine is cos, but the derivative of the inside, the minus pops out. So here we use the chain rule. Make sure you know the chain rule pretty well. And so I hope you agree that f partial y is the following expression. All right, again, we have that f and fy exists on R2, and f partial x, f partial y is continuous on R2. Thus, I theorem 67, f is differentiable on R2, so f is differentiable at the point pi 0. This is good news because now I theorem 95, the directional derivative of any u exists for any unit u. So now we know that all of the directional derivatives exist. Now that we know that all of the directional derivatives exist, we can now try to answer the question by using theorem 98. Which direction is the directional derivative the most, and what is that value of the directional derivative in which it is the most? Alrighty, so let's first try to work out now what is grad f. Remember, grad f is defined as f partial x at the point and f partial y at the point. So we've already established that f partial x, again, you can see why it's important to work out f partial x correctly, and why it is important to work out f partial y correctly. So we've done all of that. Now we're in business, and now we can say grad f at the specific point we're interested, which is pi 0, which works out now to replace all the x's with pi and all the y's with 0. And remember that cos pi, if you forgot what cos pi is, draw the cos curve. If you draw the cos curve, you can see that cos pi is minus 1. So if you calculate grad f, it works out to be minus 5 comma plus pi. All right. So far I've only got a formula for grad f, and then I got grad f at the point pi 0. So I still have to answer the question. In which direction does f increase the fastest, and find the maximum rate of increase? So by theorem 98, we can say that maximum rate of increase equals the norm of grad f. Because this is the upper bound of the directional derivative, so we're interested in the norm of minus pi, and so we got to work out the norm of this, and this works out to be root 2 pi. And then direction for most, that will be u, and that'll be 1 over grad f, the norm of that, times grad f at the point pi 0. So you can see I take grad f and I divide it by root 2 pi, and if you do that calculation, you get minus 1 over root 2, comma 1 over root 2. And you can see this is indeed a unit vector. All right. So remember, when we're dealing with directional derivatives, our directions u is always a unit vector. And there we've answered both of these questions using theorem 98. So pretty neat. So we have an alternative way of playing with directional derivatives. All right. Now, very important, as we see from theorem 95, the vector grad f completely determines all of the directional derivatives, i.e. the behavior of the function f at the point AB, provided that f is differentiable at the point AB. You can see in both examples we proved that f was differentiable at a specific point. Now, as we shall see next, it also determines the geometry of the level curves. Remember, level curves is when the function is equal to a specific value. So here we go. Let's start off with a definition. So I'm going to remind you, how do we define tangent lines? Let I be an open interval and R be a vector valued function, which is a differentiable function. If C is an I and R dash C is the vector X dash C, Y dash C, and it's a non-zero, very important, it's non-zero, then R dash C is known as the tangent vector to the curve C at that point. And so here's the equation of the tangent line. It is L is all of the points RC, so it goes through the point RC plus T R dash C. So what we're essentially saying is you have a curve. This will be the point RC, and the tangent line has direction R dash C. We saw this in 124. Now, a non-zero vector T is a tangent vector to C if the vector T is a scalar multiple, a non-zero scalar multiple of R dash C, the derivative vector. All right. Here I have another remark. Let C be a curve as defined in definition we just had, with tangent line L at point P, looking at this figure, a vector T is a tangent vector to C if and only if. So if you take another point Q on a T and you subtract the two, that Q minus P, so which is this vector from P to Q, that this vector must be a non-zero scalar multiple of R dash. So in this situation, if we consider the following vector n with components y dash comma minus x dash, and we do the calculation r dash dotted with n, remember r is defined as x dash c comma y dash c, this 2D vector, and n dash n we define as this 2D vector. If we take the dot product of these two vectors, you multiply the first components plus, you multiply the second components plus, it evaluates to 0. And we know that if the dot product of two vectors is 0, then they are perpendicular. So therefore, this vector is perpendicular to tangent line L. And we have a new word for this. We say that n is a normal vector to C at that point RC. So we can think of n as being perpendicular to the curve at that point. So let's turn this into a formal definition. This is definition 102 in the textbook. Let C be a curve as defined in example 100. So it's the tangent line at point P. If P is on the curve and T is a non-zero vector, this is very important, that T must be a non-zero vector, that is a tangent vector to the curve, then a non-zero vector n is a normal to C at the point P if and only if the dot product of those two vectors is equal to 0. Alright, so now we are ready for a theorem. Theorem 103. Let f be a function of two variables with domain D, which is a subset of R2 in an open set. If f has a continuous first order partial derivatives on D, and not only does grad f exist, but grad f must be a non-zero vector. If grad f is a non-zero vector, then grad f is a normal vector to the level curves of f that passes through the point AB. Now again, remind you that level curves would be all the 2D vectors x, y with a property that fxy is equal to k. So this is what level curves are in 2D. So what theorem 103 is actually saying is that if you have a point AB and a function of two variables and you form its level curve that passes through the point AB and you calculate grad f at the point AB, then the level curve is perpendicular to grad f. So this tells us not only about what happens about the directional derivatives, but it gives a little insight about the geometry of what happens at the point AB. Remember, f is a function of two variables. All right. Now, this theorem will be in the next theorem will be done in the next year. That will be part of part 2 of this. The theorem will be done in the next video. So please listen to the next video. And what's cool about theorem 103, somewhere I'm going to use the implicit function theorem. So if you've forgotten about the implicit function theorem, so please brush up on the implicit function theorem before you watch video 2 in this series. Alrighty. Now to finish this video, I want to end up by looking at the following example. We want to find the equation for the tangent line to the curve C with the equation x squared plus xy squared plus 2y cubed equal to 0 at the point 1 minus 1 if the tangent line exists. So I'm going to use theorem 103. Now to use theorem 103, I have to make sure that all the conditions are satisfied, that all the first order partial derivatives are continuous, and that grad f at the point is non-zero, and then I can use theorem 103. Alrighty, so are we ready for this? Yes, we are. So let's start off by, first of all, let f be x squared plus xy squared 2y cubed. So we don't have a function of two variables here. So we've got to make a function of two variables. Otherwise, the marker will say, what function are you playing with? So here we want to play with a function x squared plus xy squared plus 2y cubed. All right. Now, some comments. If I replace with 1 and y minus 1, I end up getting 1 y squared. So this becomes plus 1 minus 2 is equal to 0. So 1 minus 1 is on curve fxy is equal to naught. And note that fxy naught is a level curve. All right. So now we have established that the point 1 minus 1 lies on the curve with equation f equal to naught, where f is this function of two variables. Alrighty. Now we want to use theorem 103. So again, we need to make sure that f has continuous first order partial derivatives and that grad f is non-zero. So let's quickly work out f partial x. So we differentiate each term partial derivative with respect to x. So partial x that becomes 2x becomes y squared. F partial y. So partial y is naught, partial y is 2xy, partial y 6y squared. And now we go grad f. This is continuous on R2. This is continuous on R2. So we've got to satisfy the conditions of theorem 103. Remember, the first order partial derivatives have to be continuous, so we've satisfied this condition. So now we've got to make sure that grad f at the point is non-zero. All right, so now grad f at the point 1 minus 1 is going to be the vector f partial x at the point 1 minus 1, f partial y at the point 1 minus 1, and if I plug in, I get 2 times 1 plus minus 1 squared. I get 2 times 1 times minus 1 plus 6 times minus 1 squared. This works out to be 3 and this works out to be 4. And this is non-zero. So you've got to tell yourself and the marker that I've worked out grad f at the point 1 minus 1. It's the vector 3, 4. And this is a non-zero vector. All right? So this is a non-zero vector. So this is now important because now I have another peek at theorem 103. Then grad f is a normal vector to the level curve of f at the point AB. All right. So we want to find the equation at the point 1, 1 if the tangent line exists. So knowing that tangent line exists and that fx, fy is continuous on R2 and grad at point 1 minus 1 is 0. I want to emphasize that. So the partial derivatives are continuous and grad f is non-zero. We know by theorem 103 that grad f is normal to the level curve if xy is equal to 0. All right, and that is the level curve that contains the point 1, 0. Now it's sometimes good to draw a little picture. So let's draw a little picture. So here I have the level curve fxy is equal to 0. It contains the point 1 minus 1. And we know that this vector grad f at the point 1 minus 1, which is a vector 3, or is perpendicular to the level curve. So what does that mean? So at that point, if we draw a tangent line, let's make it green line, it will be perpendicular to the tangent line. All right, so it's not a great diagram, but I am graphically trying to explain, so it's good to draw pictures. So let's xy be a point on the tangent line. So theorem 103 says that if you take the level curve f equal to naught, and remember it contains the point 1 minus 1, and the green line is the tangent line, n is the normal line, so which means n is perpendicular to the green line, that the black line, the n, the normal line, is perpendicular to the level curve f equal to naught. So which means that n is perpendicular to the tangent line. And so what it means is the following, that the direction of the two lines are perpendicular, so the dot product is 0. So that means the following, that grad f at the point 1 minus 1 dotted with, to get the direction of the line, you subtract two vectors on the line, so xy minus 1 equals 0. So this is the direction of the normal line, and this is the direction of the tangent line. If you dot these two 2D vectors, you get 0. All right, I need a little bit more space. And so we've worked out that grad f at the point 1 minus 1 is the value 3, 4. And here, if we subtract these two vectors, we get x minus 1, y plus 1, and that's equal to 0. And now we dot these vectors, so we get 3 times x minus 1 plus 4 times y plus 1 is equal to 0. So we get that 3x minus 3 plus 4y plus 4 is equal to 0. I'm going to take it slow, I don't want to make a mistake. So I get that 4y is equal to, that's 1. So if you take it to the other side, it becomes minus 1. If you take this to the other side, it becomes minus 3x. And then I divide by 4, so I get minus 3/4 x minus 1/4. And therefore, y is equal to minus 3/4 minus 1/4 is the equation of the tangent line at 1 minus 1 to this curve. So you can see, again, using directional derivatives and using grad f in 2D, we could find the equation of the tangent line to this curve at a specific point. Now, this is the end of video 1. I will do another video on unit 3.6 where I'm going to look at the grad in 3D, and I'm also going to do the proof of theorem 103. I hope you enjoyed this lesson. Have a lovely day. Bye.